today what we're going to introduce is bridge construction. For you, out of interest, is your group project a bridge construction type? So I'll give you some background on bridges that you need to look up. Because you're covering it in your group project, if anything, what this is going to do is going to introduce you to a live case study, the Black Swan Over Bridge. This is the A19, and there was a bridge put in at that point here, where you can turn off to the Black Swan pub. And through this, you'll see how there's a number of issues that you probably have to consider for your group project. So about the fourth page over, you've got some drawings from this bridge case study. So bridges, you have got another session at some point where you'll look at the Calcrete software. Remember we looked at Calcrete slightly last year, where I think you looked at it just to see what concrete is as a material, and concrete on site, where you'll find that some of the later modules within Calcrete, there is a concrete bridge module which introduces you to the terminology and the conceptual design of, so that can be useful. For your structural design, when you come to look at concrete, you'll realise that this has actually got some concrete design also, so you'll find it'll be of use. And I think, so we've got like an IT lab where I'll show you that if you've not used Calcrete before. And within the learning materials, I've put a couple of little references for you to look at bridges. Now, get an overview of them. Like we're going to be talking about an overbridge across the A19. But you've got like beam bridges, arch bridges, suspension bridges, box girder. Has anyone installed a bridge in their career? No. But, I've put in a beam bridge. Normally if it's less than 6 metres you're allowed to put in this big slab, but it just felt like a big slab rather than feeling like it was a prestigious sort of bridge. And I've also made a point to some references that I think you'll find useful for your group project. There's a chorus student guide to steel bridge design. I've made reference sometimes to this civil engineering construction book. Like Dean Warren has like a chapter on bridge construction, and there's an SCI website. So if you look under bridge construction, there's this week and there's another week, like an IT class, and particularly the one that's not to do with this case study, there's a load of stuff from SCI, everything from abutment design to like stuff that whether you're using a steel or a composite, and then I've given you a couple of other little guides on environmental and sustainability considerations, which I think you have to consider for your group project. So we'll go through this Black Swan Overbridge, and the client that was the Highways Agency, and they passed the job to the North East sort of representative. So there was like a design and build contract, and that was won by Autolink. And so Autolink sort of look at all of the highways between like the Tyne Tunnel and Dishforth, and so Autolink had around about like sort of £46 million to do the Norton Parkway improvement scheme, like all that parkway. I don't know if you've drive along there. It's a really fast road. You can go along to Saltburn, etc. But also they were involved in the refurbishing the Tees Viaduct, strengthening works to the Hilton Bridge, and installing a load of emergency phones, And then a number of bridges were to be strengthened as soon as this, with the 40-ton truck assessment, a number of bridges failed, and so they were involved in the strengthening of a number of them. But this A19, you've all been down there. I don't know if you recognise this junction, but A19 wise, you're dealing with approximately 80 miles an hour on average. It feels faster when I'm heading down there. But we've got 32,000. So when vehicles using this each day also, which these are all things that you'd be considering when deciding what measures you're going to be putting in place. Now, it was the residents who were asking for a bridge across this area, and one of the reasons that we were putting forward was the number of accidents, and you've got like sort of details like sort of within the slides. You've got some handouts there, but there's the full presentations on Blackboard. But we've got like sort of 3 fatalities, and then we've got some serious and some slight. Now, what you'll find is that whenever something like a bridge is going to be put in place, that you need fatalities for that to happen before you can, because they're so, like, Autolink has that money to spend, and they use it as best as what they can. But you can get like a police report of all of the different reports, all the incidents, and then you can put that forward towards them actually doing some with the carriageway. The Highways Agency didn't want to put a bridge in there at first, and I think it was around about 2007 that they did this work. But before all of that, because of some of the accidents, and I think the main thing is that this was open, this junction, and people used to travel from this side across the A19 to here. And because of the incidents, in 1990, before all the bridge, they've installed street lighting. In 1998, they adjusted the lines. The whole point of that was to try and direct the traffic away from the hidden spots, but it wasn't working. They did more signing, more line improvements. And in the end, they closed the reservation to stop people from crossing over, and that became permanent in the end after about 18 months. Because the locals didn't like this, it meant that to get from one village to the other, they had to take like a massive tour along the A19. So in 2005, they did a feasibility study to see if it could be justified, whether it could be feasible financially to put a bridge in. And again, there wasn't enough fatalities, but through persistence, it went ahead. And you've got a number of the drawings for the contract. Like Autolink, they did like a topographical survey, and they did like the detailed design, and then they brought in Autolink brought in consultants, and the consultant was Scott Wilson, who did the designs, and then they had the contractor, and the contractor was Sir Robert McAlpine and Hanson Contracting. And in terms of the bridge, Cleveland Bridge did the steel work. So these are all the people who were involved in that. So we have a nice horseshoe bridge, and we have a boundary. And so, the land had to be bought, and then you've got these that's representing embankments. So it's quite a simple bridge. It doesn't go straight across. There's a slight skew across the A19, and so you've got a number of things that you can review when designing designing your bridge for your project. Bridges can carry rail, people, horses, boats. This one was designed for car and people and horses. Because of the horse use, that impacted upon the gradient. So you'll find that as soon as you start looking at the highway design manual, that you have to have like a 5% gradient, otherwise the horses can't make it up, apparently. And these bends are just to try and are designed to make sure they can accommodate the vehicles that are going to be using this. So this really determines where the bridge is crossing over. So that's where it is going to be positioned. Like, I don't know for your project whether you've got to sort of have a look and at who owns the land and decide. Say again? Yes. Well, it's usually if you're taking some land off the farmer, then they'll usually say that there's something on it so that they can get the most amount of money out of the highways, especially when they know that it has to go ahead. And so yeah, it'd be nice to know whether is it the same farmer that owns all of them, or is it a different one?
Like a forced purchase kind of thing?
It does become in the end when, like, you find that farmers tend to hold back, or any owner of land tends to hold back to try and get the most money out of something. So you've got the plan. You've got a few close-ups. So this is so you can see how it's slightly skew. We've got the elevation, and
Was that for any particular reason?
the skew was based upon the topography or the lie of the land, the way that it was. Yeah, that was the reason for the skew across the bridge. What you'll find is that there are rules about if you have a skew bridge, that you can't have any movement joints. Also, this is and also if you've got a bridge that's less than 60 metres, you don't have movement joints going across it. So all of these decisions impact upon the bridge itself. Like most bridges will just be carrying flexure or bending moment. You've obviously got shear at the abutments, and we'll look at the abutments in a moment. But things you've got to take consideration of is the approach gradient. Then you've got the height to get something under. Does anyone know what the height is? Minimum?
About 6.3.
Well, it depends on the authority. Like sort of here, we can have 5.3. Yeah, so that's what we have here. And then the choice of bridge depends upon like the method of erection, the local skills, future maintenance, and aesthetics. This is just a standard over bridge. It's not a lovely bridge unless you like this type of bridge. We'll look at some of the photos in a moment, just so that you can get an appreciation of what these things look like. But in terms of when you're looking at the costs of bridges, and I don't know, are you happy to do costs for Valeria's?
Yeah, you have to do like a general one.
What you'll find is that the superstructure, when it comes to, you've got span and you've got cost. And so the superstructure, everything above the ground, the cost obviously goes up the further you're spanning. And then in terms of the foundations, you'll find that the cost is like so. Your foundations become cheaper as your span increases.
Is that foundation per square metre kind of thing?
Yeah, and then in total, it's something like that. The overall, when you add them both together, so that's the sub. So your ideal is to try and sort of work within sort of this to get the optimum cost. But you know, you've got like sort of whatever span you've got to work to. When you look at your bridge costs, yeah, depending on the span, the foundations, and how long do we design bridges for?
How long?
Yeah, like so, do we expect them to last? Yeah, well, Eurocode 2, which is like your reinforced concrete, that's 120, no, Eurocode 0 is 120 years, and buildings are 50, unless the client specifies otherwise. I personally find that our buildings and bridges seem to last a lot longer than that, because of maintenance. But yes, so if you were designing something, it would be 120 year lifespan, according to Eurocode 0. And we've got some abutments going in rather than piles for this. In terms of the loading, you've got the Eurocode 1 to look at the loading for traffic. You've also got the highways designed. You've got the dead load of the actual bridge itself. So you've got the steel and the concrete. And you've also got the weight of the embankment all resting upon the abutments, and then they're transferred into the bearing capacity of the ground. You've got the weight of all the traffic, and you'll find that it's largely represented by like a UDL for cars. Imagine that it's just full of cars. But also you've got to look at knife load across the the bridge itself when you're looking at the shear force. And you also look at like a knife load force for skidding. So you look at sort of a horizontal braking loads, and then you've got to consider wind and thermal, which is we've not really known many issues to do with wind and thermal. Wind, which bridges had problems with wind? Okay, we've got the down in London. You've got the Tacoma, however you pronounce it. From a long time ago, the one that swayed over the Galloping Gertie, the one where the dog died in the car apparently. So we've got the client, and it's one massive team. We've got the auto link, and then we've got the consultant who's done the design, and he's passed it to the contractor. The contractor has a number of tasks that they're going through. So we've got land entry. So again, this is working with the owners of the land, and what you'll find that, like, I'm not sure within your group project whether you've got to consider all of these, but a lot of them, especially for an overbridge, they're standard things. I'm sure if you're doing bridge design all the time, it's almost like a cut and paste. Does anyone do any bridge design or road design? A little, yeah. Do you find it's a cut and paste sort of job, or do you find that you're inventing new things all the time?
Sometimes for road design, depends what options you do, I suppose.
Let's see. This is our abutment. So just again a quick overview of the abutment. So we've got our bridge, and the abutment is our foundation. And when you look at, you've probably covered moments, that like moments as force times distance possibly, with shear force and beams. And when you're designing a retaining wall, you take this point as the pivot. So in terms of load, we've got the load of the bridge, that's trying to rotate it that way. We've got in terms of the ground material, that pushes down like a triangle. So all of this load is transferred about a third up. So the weight of material pushes this way, and that's trying to rotate the whole thing clockwise. And also you have any groundwater, so there's like a hydrostatic pressure that is also trying to rotate it. Because of this hydrostatic pressure, they tend to put like granular material or hollow blocks to try and get rid of the water, so that you get a little extra pressure pushing on the retaining wall. To try and counteract it going the other way, you've got the weight of the concrete, so that would be the force coming down, and also you've got the weight of the material that's holding it down also. So when you come to design something like that for overturning, it's just a matter of looking at all the forces clockwise, and you should make sure that the anti-clockwise ones are just a little bit more, so the whole thing's not going to tip over. You might find that that you could have an extension down there if sliding is a problem. But you analyse all of this by Eurocode 7, which is the geotechnics. I'm not sure if you're going to be doing any Eurocode 7 with Chandra. Yeah, Chandra. We have reinforcement drawings. I was chatting with a steel fixer quite recently, and he was saying that civil engineers and consultants, when they come on site, quite often they can't read drawings, or if they look at the steel and then they check it against the drawings, they just don't know how to do it. Now, whether that's some of that is because it's the CAD guys who do the drawings, and that it's usually the structures people who've maybe put something together, and the actual project manager is a different person. They say that he said that a lot of times when he was putting steel in, and this is maybe a check that you could do, is that they found that all they would, as long as you got the cover from the outside of the concrete to the first bit of steel correct, as long as that was 50, it didn't really matter what they did inside of the steel cage, because they knew that the civil engineers largely didn't spot it. Has anyone had to do any reinforcement checking at all on site? Yeah. Anything complicated? Yeah.
For a steel structure for an energy waste plant, and it was the very base of it. It's probably like about 8 stories high with the steel. They went to check the reinforcement caging before they filled it with concrete, and you could have just walked on it, your foot in the floor, there was so much steel. It just looked like one plate of mesh, but they were all just individual bars.
Yeah. So how confident were you that it was right?
Well, I went to go see it more than actually.
Oh, right, yeah.
Like, for me to being able to check that out for anyone would have been so hard.
Yeah. Like when I was at WSP, I used to take the CAD guys who used to do all the drawings along to site, just to try and see what they were actually drew, and sort of so you could see it, and then they could appreciate some of the buildability or type issues, or when they're trying to put the bars in too close. There's some things that I as a civil engineer, and I don't know if you also might find, don't appreciate in terms of constructability and buildability. I think this is something that you have to highlight in your group project. Like these bars here, like starting at number 4, starting there and then goes all the way along to about here. Does anyone know what they're called? like some people call them trombone bars. And civil engineers apparently specify them all the time. And you know, you put like another one in, like that ish, to close everything up. Where steel fixers, they prefer bars on the top and then two sort of C shape, just because they're easier to fix, and it doesn't really matter which you do. Like when you come to do reinforced concrete design, you find that what's important is the area of steel that you've put in at the top and at the bottom. Like, you know, with concrete there, this steel at the bottom is coping with tension, and your concrete is coping with the compression. But if you find that the load that's coming down, if it's going to be creating too much compression for the concrete, then you have to add in steel in the top. So that's like your compressive steel. Like you've always got to put steel in the top just to make the cage go together. But yeah, it's all about the area of steel, like whether you choose one type of bar over another. Like I remember the AutoCAD guys used to have like these pages of all the different codes for steel. You know, unless you do it all the time, I never really knew myself. But yeah, it's we've got a mass concrete reinforced abutment. On Blackboard, I've given you a document that looks at all the different foundation types and all the advantages and disadvantages depending on the type of ground that you have. But here's the shuttering that's going around the concrete slabs. They say 50% of the bridge cost can be shuttering and formwork. So overall, in terms of your bridge cost, 50% of it's like temporary works that you put there and then remove, which is quite a lot. Especially if it's complicated and you've got to use like a lot of timber formwork. If there's any sort of bespoke panels. So there's our drawing, and you would be doing your checking against what they've actually put in. We've got some sheet piles just holding up the A19. Does that look nice and safe? You can see how skew the actual bridge is going to be compared to the A19. But you've got to make sure that any traffic coming down here is not going to be impacting upon your works, and hopefully it's not going to fall into that excavation. You have your abutment, and you've got at the sides of the abutment you've got wing walls. Now wing walls can be part of the foundation design. In this case it's not, it's purely for aesthetics. When you're coming along, rather than looking at an embankment, they've got a concrete wing walls. But the bridge is just resting upon this location here and that abutment. So here's a couple of pictures of the actual concrete being delivered within these wing walls. Has anyone had any experience of concrete being poured into, and does it go well? Is there things that you should recommend that we check, or? There's metal bits.
Yeah, some underneath it, like at a magnet thingy, and take it out.
All right, because they've dropped in.
Lots over time and cracks.
Yeah. And is there any reason why they pump it like right down the bottom rather than just drop it from height?
Stop like getting air bubbles and stuff.
Yeah, it's just to stop the separation of the like all the aggregate just catching in one sort of area. Plus, like pouring concrete in can impact on can knack the reinforcement cage. The concrete is a C 3240. Does anyone know what it means? What is a C 3240?
Isn't that to do with the strength?
Yeah.
That's the range between 32 and 40 newtons.
Yeah. In the UK, we use that one, this 40. So it's 40 newtons per millimetre squared, and that's based upon a cube. We do our cube strength. In Europe, because we're in Europe now, they test a cylinder, that's the 32. So you just get different values. So when we call it a C35, our 35 would be sort of there. So they've got so we've got a C. Has anyone seen any other letters in front of that for rather than C? You can have LC, which stands for, which is like a lightweight concrete. I've never been on any jobs where they've used anything other than just the straight forward concrete. Like when you specify concrete, sometimes they might say, you might have terms like where it could be an RC for reinforced concrete. When you're specifying, like normally foundations, we tend to put in at least a 35. The reason being is when we put in an RC 35 or a foundation grade, it tends to come with chemicals that protect it from the environment and like everything that's in the ground that can damage the concrete. So there's our reinforcement bars in the wing walls before the shuttering goes up. Then we've got a nice concrete finish. How do we repair a concrete finish if it's naff for a bridge? What do we do? Or what do people? How do we? So we've got we've got a concrete finish. How do we repair it? Say again. A bag wash.
Yeah.
What's that?
I don't know if that's the technical word.
Oh yeah, no, that's all right. So a bag wash. What's that?
It's like a very wet concrete. You just dab it up and just fill the holes in. But it's like a
Fill it in with what? But what do you fill it with?
Just like a very, very wet concrete.
Right. So you don't you haven't noticed whether they get a product by a company called Seeker or anything like that. It's just you just get some concrete and right. Okay. Yeah, it'd be worth having a look at the specification to see whether you're allowed to do that. But yeah, I'm sure everybody has their different ways of approaching that. But people are flying past. So it may be that for embankments that it's perfectly fine to do sort of that technique, and it's because you've got like air holes and all this type thing, or there might be some honeycombing where you can see the aggregate.
What would you do then in that situation?
Whenever I've done concrete repair, I've always worked with a company called Seeker, where you get their grouts that can adhere to the concrete and make sure it's not going to pop off. Because sometimes if you just put concrete in a hole, as soon as you get a bit of rain and then the frost, it'll just pop it off. However, a lot of the Seeker products, it's a different colour to the concrete, so maybe it's getting some concrete and rubbing it in with your 5p bag is the better option for blending everything in. In the end, you've got to make sure that you've got that concrete cover to your steel. This is the sort of the embankment side of the retaining wall, and what we have here is because, you know, I mentioned about the pressure from the ground material and the water. Quite often you have some form of drain at the back, so all of the ground material would be containing water, and that comes down the inside through these hollow blocks, and there'll be a drain that just takes the water away. The black is a bitumen paint, again to stop the water from going into the concrete. You'll find that all of the chlorides and all the salts and all the stuff that we do to stop frost, all those chemicals impact upon concrete and steel. It's very bad, very bad. But yeah, you've got about two coats of bitumastic paint. And then on top of the retaining wall embankment, we've got the connections that we're going to be putting our bridge onto. So you've got the detail there. So there's the top of the retaining wall, and then we've got our reinforcement, and again you've got the C, which is representing our cover, and it's like a little plinth which will be spaced to jack up the bridge should we need to replace the bearing. Have you got a specified bearings at all? Like, you know, when you've got, like what I'm saying there is that if you've got the bridge on top of the retaining wall, you have a bearing here so that if there's any sort of movement. But what happens is that these bearings tend to only last 25 years, so you have to put a jack in there somehow and lift up the bridge and replace these. And in terms of the different types of, has anyone installed any bearings? What were they called? No one at all? Yes, the one I've never pronounced. What's that? It's a bit like a rubber, isn't it? I don't know if you have to specify this for fill areas, but yeah, so you've got the elastomeric bearings, and it looks like a bit like a, what do you call those? It's a College Street. We've just got like different layers of this rubber material that when the bridge is moving in terms of moisture and thermal movements, it's just bending across. You can have all of these rocker bearings, where you can have a steel plate, and that's attached to the bridge, and that's attached to the retaining wall. You can get roller bearings. So if you covered things like pin joints and roller joints in structural mechanics, like when you've got a beam, you might have this symbol here that represents a roller, and what you can have is a steel tube where your bridge is attached to one end and your embankment is attached to the other, like Gateshead, the Gateshead Bridge. That, what was it called? The Eye. Well, that sort of shape.
What's the
Millennium Bridge. Yeah, my brain's gone dead. That bridge, I believe it's Gateshead Bridge, and it's fixed here, so it's actually attached to Gateshead. If the sun shines and it expands, it would push Newcastle away, which is what the Maddies would want. But what you have to do is that you have to have some form of a roller, so that if there's any movement, it can just roll slightly. So these are like different types of bearings. There's Yeah, and all you got to do is make sure that the movement is not going to be greater than, you know, this like moving right over here and then dropping down. So, you know, bridges are maintained. And I've got some images looking at the steel work, which you can have a look. We'll have a look at the photos first before we start talking about this. But this is all the bracing in between the steel work to stop it from twisting. And you've got the details of how the steel beams are joined together. Cleveland Bridge did it, so you've got, again, you've got an I beam, and it's a composite bridge, so the concrete is on top, and those steel beams on that last page, you can have braces to stop any like racking of the beams. Quite often you can't get the full length beam, so you have to join it together, and when you join it with the web, we've got a plate here with 1 million bolts, and like all of these bolts are high strength friction grip, or HSFG, and you'll find that steel bolts, just like in buildings, have to be torqued to a particular, you make sure that you don't overstress them, but they have to be torqued to a certain value. There's some nice pictures of steel, and that is the steel for this bridge. And so one, I've never been to check for steel. Has anyone been to check their steel at where it's been fabricated? You know, a lot of times it just arrives, and I've checked it when it's arrived on site, and in where maybe the coating to protect it has been chipped off, and they've had to touch it up. But this looks like well, it looks like weathered steel, a bit like the Gateshead Angel. That's like the latest trend. Have you noticed we've got that weathered looking steel in the just outside? Does anyone put anything like that up? Hmm? Oh, there's lights. Are there what? I think it's just art. I don't know. So steel's got a tendency to corrode, and you've got to make sure that you design it correctly. And Cleveland Bridge were brought in to fabricate these. It's a 41 metre span. You'll find that typical span to depth ratios for bridges is that you'll have L over length over 20 to L over 25 in terms of the thickness to span. You find that in terms of the costing of a bridge, it all depends upon the fabrication and the particular cost of steel. So when you come to cost of bridge, 40% is the steel itself, 40% is the fabrication. That's how much it's costing them to make the whole thing. And then you've got 10% is the corrosion protection. And then 10% is the erection. A lot of times the Cleveland Bridge would be erecting.
What about the temporary works? Got 50%.
No, that's the cost of the bridge.
Oh, right.
Yeah, steel bridge. Yeah. Like this, well, the steel part of the bridge. So, and what you'll find is that you've got like one man hour equals the price of like 30 to 70 kilograms of steel. And you know, you'll put in a design, and your beam might be so thick in terms of the flanges and the web itself, and what you'll find is that like Cleveland Steel will take your design and then possibly propose a thicker, or the depth might change slightly. They might put some stiffeners in where just to improve the shear, and all of these options are just weighing up the amount of steel compared to how long it would take someone to fabricate it. And what they're trying to do, they're just trying to reduce the cost of the bridge, because like each stiffener can take like 3/4 of an hour to put in. The bridge, as you can see, has a slight camber. The idea is that you put your bridge down, and then, because if you just have a straight bridge and you put it down, it could just sag, and then you just end up with a swimming pool in the middle. In terms of testing things, you would have to test all of the welds, and you find that like tests are not done within 48 hours. You've got a mark there to show we'll test this area. It's the same for all of the steel. You've got the shear studs on the end of the beams. The design is composite, so you have shear studs on the top of the beams connecting the concrete slab to the steel beams, and also the end of the beam is connected into the concrete. Also, you have to test them. You take a British standard 2 kilogram hammer and you smack it, and you test approximately 1 in 50, and they shouldn't break off. They might bend a bit, but that's the technique for testing shear studs. So Preston's arrived with the bridge. They put the walkway, the safety edging onto the bridge while it was on the vehicle, rather than doing it at height, just to make everybody safe. And then we have our crane. How much is a crane to hire? A lot. It's £2,000 a lot. That's what I've got written down. I've never hired a crane. I'm only told. Yeah. So it's but it all depends upon the crane and the lift that you've got in at what time. Do you have to close the roads? Yeah. It's what happens if you were doing putting a bridge over a railway line? Do you have to stop the trains? Because you don't get trains that often, do you?
Well, I think most lifts are done at night.
Yeah. But yeah, you'll find that you have to get permission to close everything for a short while. You can't do it sneakily. We've got the outriggers, just make sure everything's not going to fall over. Has anyone had a crane collapse on them? No? Not on them, just like on their site. I have. Nothing to do with me. But yeah, the ground was too weak, and the crane went over. I had another one where the crane was going over some trunking, and there was precast concrete like manholes, and it went into the manholes. There you are, all my favourite pictures of the beams going up. Have you done centre of gravity yet in structural mechanics? So they got 2 no, and you got. So when you have, like, I think AutoCAD does this automatically, but if you have like a piece of steel that you want to pick up, and you've got to, like, is that what AutoCAD does? It gives you like points to pick it up from, to make sure it all comes up nice and equal. But centre of gravity is all about working out where the mass of the material passes down through, and you can. Yeah. I don't know, when you see like grand designs and things like that, they just seem to like give it a go. Especially when it's glass, huge pieces of glass. I saw one when they were making like a big thick piece of glass, not grand designs. It was like an engineering one where it was like a big curved piece of glass that they were sticking in front of like a shark tank, and I don't think it was glass though. I think it was some form of perspex. Yeah, that was it, perspex. So they did it at night time, which is just like you predicted. So it just makes all my pictures dark. So the that image there is just showing the cross bracing again, just to make sure that any lateral movement won't make it rack over. So we've got it being lifted into place. I do have another little video. This one. This is the bridge being put in near the Newport Bridge. But they were putting a bridge over a railway, and based upon, well, they couldn't get too close to the railway line because they didn't want to damage it, so it had to be a distance away. So they brought in this massive crane to put it in place. Does anyone know what this? Has this bridge got a name? Do you know which bridge I mean? It's quite a new one near the Newport roundabout to take you across. Towards like St Hilda's and all that type of. You might see it.
Well, they've changed the roundabout where that Phoenix Church is. And the old
Yeah, near the Phoenix Church. So here they needed a crane to make the crane, and they also had to put in piles underneath the crane to support this crane. I understand there's either one or just a few of these cranes. Oh, missed it. So they did the whole thing in 2 lifts. Yeah, so the Newport roundabout's like over here. And I've got written somewhere of how much it costs to to stop the trains, but I can't see where it is. If I find it, I'll send it through. It's quite shocking the amount of money it costs per hour to stop. So that was just that bridge going in. It's very, very short. Yeah, so the new port is round about here, and they had to put some piles in. So back to our bridge. So we've got some sort of K bracing. These shear studs will fit into they'll concrete up the abutment. They had people on standby just in case the bearings didn't fit. And they've got some steel shims, so as you know, they can get it right sort of horizontally in terms of the height, depending on how much it dropped. So it's very similar to putting in a steel columns for a building. And these are POT bearings. They're the most common type of bearing that are used on bridges. So this is the pot bearing. Then they'll. And this is so the new port bridge. We took the first year students to have a look at this. But yeah, this space is so that they can jack up the bridge and replace and maintain the bearings. And then it's grouted up with a high strength grout. This is the bracing, and underneath is permanent formwork. I've put a little link on Blackboard about the permanent formwork. It's called EMJ. Does anyone else call it anything else? So he's actually standing on it. We've got our 1,000,000 bolts going in. Don't know how many bolts it was. It's like a 10mm gap between the two beams. So that's the permanent formwork there. So you can actually sort of stand on that. It's a glass fibre reinforced plastic. There's like a sealant in between the formwork and the steel to stop the concrete sort of dripping down onto the ground below. There's the detail of the top of the flange going into the concrete. All the steel is standard high yield. It's not stainless steel. Stainless steel is about 4 times the cost. Having this permanent stuff just gets rid of having to put loads of formwork underneath when you're casting the concrete in. Then they'll put the concrete on top of the concrete will be poured in here, and then the concrete will rest straight onto the shear studs, because it's a bit like are you thinking of like when you've got like Wrigley tin and you can have the shear studs put through here. It's not required in terms of this design. These bars here are holding up the support that everyone's going to be working on. And then in goes all of our bars. So you check that against the reinforcement schedule. So we've got all of these extra T stuff going in the top and B going in the bottom, and you've got your spacing. So you've got 150 spacings, and then you've got different size bars. The cover's about 30 to 50 millimeters, and the bars are size 20 or 25. There's larger bars at the edges. And you can see the shear studs on the top of the beams which connect the slab to it. So we've got our concrete vibrating plate to get rid of the air, to make sure that the steel is protected from environment. Those on top are holding the Say again? You'll find that the consistency of the material, if it's stiff enough, you can pour the concrete. You can pour concrete where you can put concrete on almost vertical. I think when we cover high-rise concrete frame buildings, I'll be showing you one where they're casting concrete, or they're trying to get concrete on a sort of like a 15-degree sort of slope, and you'll see how it starts off too sloppy and it all drops off. And it's that Discover engineering guy, the guy who sort of throws all the bolts on TV, and then the next mix that they do is too thick, and the pipe explodes. It's quite a good video. But you've got a very, very fine slope here, 5 degrees. So we've got our concrete slab. This is just showing the bitumen and also the pathway. There were some cracks in the concrete, which we're slightly worried about. Concrete does crack. You're allowed like 0.3 mil cracks. But when they drilled down, they found that the crack was just on the surface, so it wasn't all the way through the slab itself. Then they put a bitumen on top to get water away from the concrete. They're just walking along the edge there to make sure that they don't, on felt, to make sure they don't damage it. These here are the handrail is an equestrian. They're designed so that when horses are riding across, they don't look down and see loads of cars and rear up and throw you off. So they're designed special equestrian galvanized steel parapets. And that's the final bridge. They did some landscaping, obviously, around the side. They planted some trees and some bushes. Has anyone seen this tape before? Like this filter tape? Like when you put when you have an embankment, it's going to settle over time, and they have this machine that punches in, a bit like goes to depth, a filter tape, and what happens is that the water that is in the embankment goes to this filter tape and then comes over to the surface, and it speeds up the amount of settlement. So that's what that is. This little image here is showing that if you did have a sensitive, if you had like a railway and you didn't want to make sure that the weight of the embankment is not going to impact upon the rail, you can have polystyrene blocks. So that you get huge polystyrene blocks, and you can make up the embankment with this polystyrene. But that's, yeah, the filter strips. And then we've got the road going on, all the, and I think in terms of sustainability, they put in some attenuation ponds. Have you covered any sustainable type stuff for getting rid of drainage? Like anywhere where you create a solid surface means that when the water arrives, it's going to move off much faster, and you have to try and make sure that you deal with that. And you can either put it into the local drainage system if you're allowed to. If you're not, it may be that you've got to